Good morning. My name is Raikhan Tokpatayeva, and I am a lab and staff. I am lab and research staff at Purdue University. And today I will present some of the outcomes of our study on potential utilization of non-traditional ashes, such as ground bottom and fluidized bed combustion ashes in concrete mixes. And this study is a part of the research project on possible utilization of non-traditional and natural pozzolans, which is being a collaborative work between Purdue, Penn State, and Clarkson University. And for this part of the study, I would like to acknowledge the contribution of Penn State group, led by Professor Ajay Bepur, and also from Purdue University, Professor Oleg, and PhD student Alberta Castillo, which both are here, and undergrad helper Bibigul Shmabai. In the motivation behind of our study is, for that I can also refer to the previous presentation done by Dr. Hutton, is an increasing shortage of traditional SCMs, which launches the exploration for any good alternatives. But however, the search for the alternatives, which might be non-traditional or off-spec sources, creates more challenges. For example, revisiting of some of the test methods and development of the optimum mix designs. In our study, we started from the characterization, first the characterization of those raw ashes, then tested them for the pozzolanic reactivity, and lastly evaluated their performance in concrete mixes by testing for mechanical, transport, and durability properties. So today I will share with you some of the outcomes of that study. In our study, we used three ground bottom ashes, which we put as a GBA1, GBA2, GBA3. They differ from of mainly the calcium oxide content, being the minimum 2.8% and maximum 23%. Then we used two fluidized bed combustion ashes, FBC1 and FBC2. By oxide composition, as you can see in this ternary diagram, all ashes appeared to be in the area of traditional ashes, and the calcium, by the calcium content, all of them except GBA3 can be categorized as class F ash. However, by the sulfur trioxide content, only FBC2 was appeared to be out of spec, having the value as 8%. Also, both fluidized bed combustion ashes showed high values of loss on ignition, which can be connected to the noticeably high carbon content. The amorphous phase of the ashes were in between 18 to 64, around an average 64%. By particle size, all ground bottom ashes were similar to each other, and also they were the finest among all old ashes. And in contrast, the fluidized bed combustion ashes were coarsest, even they were coarser than the cement that we used. And according also, if we will take a look at other properties, according to the strength activity index, all of them met the specification limits, were all above the 75%. However, in case of FBC ashes, the water demand was higher than the limit value, which we will see later on, that also affected the slump of the mixes. Then the pozzolanic reactivity of the ashes were evaluated by the R3, so-called R3 test. For that test, the paste samples were made by using the material. In our case, it's the ashes, that bottom and fluidized bed combustion ashes, some calcium hydroxide, adding some calcium carbonate, and alkaline sulfate solution. The whole procedure of this test is specified in STM C1897, so I will not go into details of the test, but as a result, the pastes were evaluated, the pozzolanic reactivity of the pastes were evaluated by the chemically bound water, heat of reaction, and the amount of consumed calcium hydroxide. And in addition to that, also the samples were acid digested. So it was for the acid dissolved material. In respect to both total heat and chemically bound water at 7 days, all ashes, both GBAs and FBCs, they fell into the moderatively reactive region, which were specified by the RILM 267 TRM. And but GBA, among all of them, GBA3 and FBC1 were the least reactive. And same trend can be also seen in case of acid dissolution test. Then, after testing the pozzolanic reactivity of those materials in this more mimicking and synthetic environment, we wanted to move to the more realistic cementitious system. So the heat of hydration and also the consumption of calcium hydroxide in cementitious system was evaluated. For that, the paste samples with 25, 30, and 35% replacement and with 0.42 water to cementitious ratio were used. And as for the reference point, the pastes with inert filler as a ground Ottawa sand were used. As it's shown on the right-hand side graph here, even though the total heat of all the ground bottom ashes generated at 7 days were lower than the mix with just a plain OPC paste, but they were all higher compared to the system with inert filler, so showing some pozzolanic reactivity 7 days. Also, the blending of these ground bottom ashes into the OPC, it didn't cause any modification or any changes to the heat flow curve of just the plain OPC, which is not true in case of fluidized bed combustion ashes, and especially in case of FBC2. You can see that first of all the dormant period got elongated, whole main peak got shifted to the right, and also this second peak, as we call it, sulfate depletion peak, just disappeared. Also, both FBC ashes showed some pozzolanic reactivity, which we can judge by the higher total heat compared to the system with inert filler. Also, as for the CH consumption in cement pastes, it was determined in respect with the, again, the cementitious system with the inert filler, as As you can see from the graphs, the consumption of the CH, of the percentage of out of available CH was increasing over time, and it was significantly increased at later ages. And again, here, similar to the R3 test, we also found out that among all the ashes, FBC1 and GBA3 showed least reactivity, at least related, at least regarding to this, to the CH consumption. Also, we performed some penetrometer test of the mortar samples, and the FBC2 ashes compared to others, they here again you can see some retardation compared to the plain OPC, but others were more or less close to the plain OPC. Also, I'd like to note here the loss of slump, the result of the mini slump test on the mortar samples, and it was for the we can say for all of the ashes, but maybe it was more significant in case of fluidized bed combustion ashes, and it was more prominent when we were increasing the replacement level. The compressive strength was also evaluated for the mortar samples, and also it suggested the improvement of the mixes, the performance of the mixes at later ages. At 7 days, you can see that it is some of them comparable, but most of them are lower compared to the plain OPC, but at 28 days, they were catching up. Most of them are catching up with the plain OPC system. And also, similarly to R3 and also CH consumption parameters, for the R3 test parameters and CH consumption parameters, both FBC1 and GBA3 here again performed worse than others. So here, sorry. And after all characterization and tests on pastes and mortars, the concrete mixes were developed and tested for mechanical transport and durability properties. For both compressive and compressive and here flexural strengths of concrete samples with 25% replacement, all the ground bottom ashes and the FBC fluidized bed combustion ash mixes showed comparable or lower values in respect with the plain OPC at early ages, but as you can see from the compressive strength results, they started to be catching up or even being higher at later ages. Also, the water absorption test was also performed on the concrete samples, and according to that, behavior of the ash concrete mixes was found to be more or less comparable to the plain OPC mixes, but for the secondary absorption being slightly lower in some of the ashes. As for the drying shrinkage, which was performed on the drying shrinkage test, which was performed on the mortar samples, the FBC1 showed a bit higher values compared to plain OPC mix, but all the ground bottom ash mixes performed more or less similar to the reference. Also, for the transport properties, we tried to evaluate through the formation factor. And as you can see from the graph here, the formation factor of all the materials at the beginning, at early ages, were comparable or a little bit less than the plain OPC samples. However, as time goes, as the curing time progresses, all GBAs were higher, showed higher values, being at after 91 days, being in the region of freezing and thawing and de-icer safe region. But FBC1 showed similar performance to the plain OPC mix. Also, in our lab, we also performed the salt scaling test using two least reactive materials, as we have seen before in previous slides, that they were FBC1 and GBA3. So by using them with 25% replacement, we made concrete slabs. So here you are seeing those slabs at 0 cycles, so before the exposure to the chloride and freezing and thawing condition. And this is after the 50 cycles. So compared to the reference, they performed worse, and they, by the visual ranking, they fall into the 4 and 4.5 level, which is quite comparable to the traditional fly ash performance. As you can see here, we have two mixes with 30% of fly ash with different water to cementitious ratios, and both of them also performed compared to the plain OPC worse, and also ranked with the 4 and 5 levels. So the ashes that we use, those non-traditional ashes, also behaved like a traditional ashes in this case. Then, in addition to the scaling test, we also wanted to test to see the interaction of the paste matrix with chloride environment, with rich chloride environment, in order to see, to check for the chloride binding capacity, binding the chlorides into the non-harmful phases, such as friedel salt, as you can see those in the SCM micrograph here, and as well as the potential formation of the harmful phase, which is called the calcium oxychloride. You can see here the large needle-like crystals of the calcium oxychloride deposited in the crack in the concrete matrix. And for the evaluation of the chloride binding capacity, we followed the same regime as for the scaling test. As for the calcium oxychloride formation, there is the AH-T 365 standard, so we followed the instructions of this standard. And the result, as you can see on the in this graph, all of the ashes they showed much lower calcium oxychloride formation, the amount of calcium oxychloride compared to the reference. However, you can say maybe most of them, they were close or above the critical limit specified by that standard. However, when we increased the replacement level, that value was decreased. And the calcium oxychloride formation is mainly can be associated with the available calcium hydroxide in the system. So as you can see here, there is a good agreement between the the amount of formed calcium oxychloride and then the calcium hydroxide in the paste. So it also relates very strongly correlates with the pozzolanic reactivity of those materials. As for the chloride binding capacity, we evaluated it by the amount of the Friedel salt. And as you can see, it was for all the ashes in the same environment and the same regime of testing. All the ash blended mixes showed higher amount of Friedel salt form in the mixes. And this, the amount of Friedel salt formed can be correlated also with the alumina content, and especially with amorphous alumina content. And if to summarize all the results that I showed here, so first I would say that all the ground bottom ashes and fluidized bed combustion ashes used in this study met the requirements of STMC 6018. However, there was some slightly deviations, especially for the sulfur content, water demand for the fluidized bed combustion ashes. And according to the pozzolanic reactivity tests, all the GBAs and FBCs can be classified as a moderately reactive and with reactivity comparable to the traditional fly ashes. However, there were some outliers among all those ashes, and they were one of the fluidized bed combustion ash, FBC1 and GBA3 being the least reactive. And compared to the OPC mixtures, we found out that the blending of those ashes caused some slump loss, and it was more prominent in case of fluidized bed combustion ashes, and it was increasing with the increase of the replacement level. If we will judge by the performance of these materials by the calcium hydroxide consumption, compressive strengths, you can see that they start performing at later ages, starting to show their potentials at later ages. But in case of concrete, in concrete system with the 25% replacement that we used, those ashes they performed quite similar to the OPC concrete. Thank you. If you have any questions.